Right, you can start.
Okay, we do a job McCall interview. Come up to your house and we've got 100 calls now for time. Okay, so John, what topics do you currently lecture and research about?
I lecture a module on adaptive intelligent systems, and that's related to my research, which is the naturally inspired computing and probabilistic modelling.
So could you go more into adaptive intelligence?
Well, adaptive intelligent systems are systems that adapt to data or knowledge or changing circumstances in an intelligent way, and that intelligent way is based on machine intelligence, which analyzes data, looks for patterns in there, or evaluates solutions to a problem, and sort of according to some predefined criteria and constraints, and then searches a big space of possibilities and then tries to select the right one. So basically the idea is that for businesses that are making very complex decisions, scheduling for example, or controlling the subsea environment, these adaptive intelligence systems can help to take out a lot of the complexity of those decisions and come up with very good options very quickly in response to dynamically changing circumstances.
Yeah. So is that like McCall section?
Yeah, well, there's a whole bunch of techniques that can be applied, and a lot of them are inspired by the way natural systems solve problems. So ant colony is one such example, which is inspired by the way that ants go out and forage for food. So the ants leave trails of pheromone. There's famous experiments done where they had an ant hill inside a tank, and they had a gap and then a bowl of sugar, and then they had a ruler stretched across, and then they had a kind of longer path, and the ants started out milling across both paths, but very soon they were running up and down the shortest path. So essentially they had solved a very simple version of the shortest path problem. And the way they did that was that when they put down these scent trails, the scent evaporates over time. So on the longer path, there was more evaporation of the scent than on the shorter path. So the shorter path smelled more attractive to new ants coming along, and therefore they were more likely to go down that path, and therefore they were more likely to get excited by the sugar and lay down pheromone. So it was a self-reinforcing thing, and therefore that's how the ants solved the problem. So in ant colony optimization, the classic example of that is the travelling salesman problem, where you're trying to travel. A salesman has to travel between a number of cities. They can go by any route, but they've got to go by the route that means the least travelling time. So you imagine you have to go to Glasgow, Inverness, and Edinburgh. You wouldn't go to Inverness, then Glasgow, then back to Aberdeen, and down to Edinburgh. That would be a bit daft. If you went to Edinburgh, you'd probably go to Glasgow next. Well, the travelling salesman problem is solving that for large numbers of cities, and as soon as it gets up to 40, 50 cities, it becomes quite hard to find the optimal solution. So ant colonies optimization does this by each ant constructs a path initially at random, and at the end of that, the ant calculates how long the path was. So some of these paths would be a completely stupid paths, so it starts at random. So it calculates how long the path was, and then it inverts that number. So the longer the path, when it inverts it, the lower the score it gets. So you get a score which is 1 over the distance, right? So then that score, the higher that score is, in other words, the shorter the distance of the path, the more excited the ant gets, and it lays down pheromone across the path that it was followed. So each path gets a reward. So each point of the path, so if you happen to go from Inverness down to Edinburgh, that might tend to be something that appears in a lot of very long paths. So it wouldn't tend to get very much reward, whereas going from Edinburgh to Glasgow is a short segment, so it might get a lot of reward because a lot of that more ants might use it. So as a new ant comes along, when they're at any city, they've got an option to go to any of the other cities they haven't visited yet, and there will be amounts of pheromone laid down across those paths. So essentially, there's probabilities that the ant will select that path.
Yeah.
So it then rolls the dice, and the probability of selecting each path is then weighted. And over time, of course, then eventually the ants converge on the shortest path. So that's the idea. So that's actually used in quite a lot of different areas.
And so what pushed you to use your mathematics expertise in modelling to move that into organisational systems?
Yes, that's right.
So what pushed you to make that jump between your modelling into your organisation?
Well, I mean, I originally was a pure mathematician, so I did a subject called algebraic topology for my PhD. And then, as is the way with life, when you leave university, you get married, and lots of other things interfere. So I spent some time as an accountant, and then got a job in this department as kind of a half mathematician, half computer scientist, and got interested in cancer modelling. And so we were modelling the effect that a treatment had on a tumour. And so your objectives to either reduce the tumour without killing the patient, or palliate the tumour, keep it to a manageable size, and extend the patient's life as long as possible without having lots of toxic side effect problems and so on. So there were two objectives there, and modelling that was one thing, building a mathematical simulation was one thing, but then you could ask the question, well, what's the best treatment? There was quite a lot of work on trying to find the best treatment, but as you add more and more constraints, maximum drug doses and so on, it actually becomes very difficult for mathematical optimization techniques to solve that problem. So I got into genetic algorithms because they're very good at solving highly nonlinear problems with lots of sort of discontinuous cut-offs and so on. So they're quite hard to solve with traditional techniques that get stuck. You can't just sort of climb up a hill in a particular direction. So genetic algorithms work very well. And then I got into the whole interesting idea of, well, how do these things actually work and what drives them and so on. So I spent the last 15 to 20 years thinking about that.
Okay. So I emphasise your research on chemotherapy. You also do some research in the oil industry. I'm wondering where your interest in that came from.
It comes from the interest in applications. Sometimes comes from me. Sometimes I think, I think that problem can be solved by activities. Other times it comes from industry. So a particular project I've been involved in recently was with modelling rig market data, and the aim there was to help people to go thinking 5-7 years ahead of time about drilling operations and what rig are they going to use, what kind of circumstances and so on, how long is it going to take, and that kind of thing. So they're really looking at the market and weighing up cost versus time taking versus reliability and so on. So there's a whole bunch of different factors there. So one area that I'm particularly interested in is when you've got lots of data and lots of different variables, and you're trying to mine that for patterns and work out how these variables interact, and then use those models to make predictions. So that's particularly suited to that area. So in that case, the company approached me, and we did a 3-year project in that. Hopefully that will soon be a software tool that's out there.
Fingers crossed.
Yeah.
So how does your research in computer intelligence, such as small intelligence and McCall optimization, how does that help you in your research into chemotherapy?
It's more that, you're talking here about multidisciplinary research. So I work with cancer experts who are treating actual patients. And what they're interested in is understanding, they build their decisions about how to treat patients on experience and on medical literature and so on, which is also largely based on experience and patient case data. So initially I got involved in mathematical modelling of what was going on, and they were interested in that because it helped give a different perspective that either supported or rejected their decisions, or it was models that they could then ask questions of, what if I give my best drug last rather than first, and that kind of thing. But more recently we're much more interested in looking at patient data, almost in the same way that they do, but then building models that can then show them relationships between variables that we might not have understood. So we've got a PhD student we're working with prostate cancer specialists at Aberdeen Royal Infirmary, and there we're trying to. Prostate cancer is it's an uncertain diagnosis, and the treatments for it, surgical treatments for it, are not always that successful when you're talking about old and infirm patients and so on. So there's a difficult decision to be made about whether you actually operate or not. And if you can guess that the cancer has already spread, then you tend not to operate because you tend to then use chemotherapy or something like that. So trying to infer from a few fairly crude physical tests and lots of patient data whether or not to operate is one of the things that we've been working on.
Okay. So with all your research in mind, what do you see for the future of artificial intelligence and computer systems?
I think there's a huge future because I think more and more in society we're getting into very complex systems, and those are very hard, and they change very quickly, and those are quite hard for slow-moving human brains to calculate with. What these systems do is they calculate very fast and are very good at finding good solutions, not necessarily the very best solution, but good enough solutions. And I also think that in the current economic situation, we've got to the point really where it's not easy to make money anymore by just going out and getting resources and digging them up, making something and turning into cash. So if you want to create wealth these days, you've got to do more for less resource. So I actually see intelligent algorithms as good ways of, by optimizing, saving resources, making things more efficient and effective. So I think there's a big market for that. And I think the third aspect is that everything now generates data. We're in an environment which is increasingly being pervaded by various sensors, signals, and so on. And that will become, that will just accelerate. So you've got all this information and data kicking around, and we need things that are going to interpret that from us. So a big move in computing is augmented reality. You can hold up your smartphone and you can have things placed on an image and so on. Well, everything's going to be augmented by data, and therefore we will be in a tsunami of information, and therefore we need good glasses to put on to be able to understand that environment. And adaptive intelligence systems, I think, can help to mitigate that for us and help us to navigate that in exactly the same way as control systems are already helping people to fly, inherently unstable aircraft and helicopters and so on. So they can smooth out some of that regularity and present the essential decisions to us. So I think there's a lot of scope in the future.
Okay, well that's perfect, thank you.
Thank you.
Very much.